start. Here we go. Okay, so first thing first, since I was looking this up a little bit earlier for the early lab, our final exam is, because the lecture of this class is from 7 o'clock to, the start time is between 7 and 7:55. So that means our final exam time is on the 15th of May on a Tuesday, 2 weeks from today, from 8 to 10 p.m. So I cannot move that one, okay? So this has to be the only time, and the exam is going to be here in Rave Hall. It's once again open book and open notes, so you can bring anything you want to. That includes all the sample programs that we have done in class, all the solution to the homework assignments, and anything that you find on the internet, anything that you write, anything that you type, screenshots from my videos, whatever. Is that okay? You can bring a scientific calculator with you, but otherwise it is a no electronics kind of final exam. And we'll go over practice questions next Tuesday, which is exactly 1 week from the final exam. All right? Is that okay? All right. So with that out of the way, I'm going to close some of these windows because I don't need those anymore. This one I might want to keep for the late lab. I'm going to keep this one for the late lab. This one I don't need anymore, so we'll get rid of this one. This one I don't need anymore. Get rid of that. This one I don't need anymore. Let's get rid of that. And this one, we don't need that anymore, but I'm going to remove it because I'm going to reuse it. There we go. So what we'll do today in class is I'm giving you an example of how to use structures and how to write code related to structures. Okay? We started that topic in the previous class already, so this is more or less a continuation of what we talked about last time. So in this case, we're going to have a struct X here. Okay, we're defining a structure itself, and remember, a structure is kind of like a class, except everything is public. You cannot have methods. You can only have member attributes and values. So that's kind of the restriction. And I'm going to use a v for the value, and we'll use struct X as a pointer, and we'll just call this next. So basically in this particular class, during the lecture, I'm going to use a linked list, a linear linked list as an example. Okay? So what we'll do is we're going to define a few global variables because this is how we're going to do it in assembly for the homework assignment. So I'll give you some global variables defined as struct X's. So the first one, I'll just call that N1, okay, or N5, N3. Okay, there we go. So N3 is a struct X node, and you can use curly brace to provide values to a structure. You can make initialized structures in C. So in this case, N3 has a value V of, let's say, 2, and a 0 for next, because it is the last one. Then we have another struct X called N2. And N2, I don't know, for the value part, we can have 5 this time. And for the address of another struct X, we'll have the address of N3. And then we have N1, and let's say it has a value of 16, and the next has the address of N2. And we'll just call this all the initialization. Are there any questions about this part here, especially on line 7, 8, or 9? Are there any questions about the purpose of these 3 lines and what they actually do in C code? Yep.
So this is just a singular linked list going from N1 to N3?
Yep. All right, so we have a main. And I do intend to compile this program just to make sure that it does run. So I'm going to include the proper header file. And then back here we have, let's see. Since I'm going to demonstrate this program in GDB, I'll just go ahead and write a loop here. So we have struct eggs ptr, and ptr is initialized to the address of n1. Then we say while ptr, do the loop here. And in the loop, the only thing we're going to do is to say ptr becomes ptr points to next. There we go. So for those of you who are in the early lab, this resembles some of the things that you have to do, but yet it is not identical to what you have to do in the homework. So before we move on and actually talk about the assembly code implementation, we're going to compile this program, run it in GDB, and find out exactly what it does. Okay, and also we'll find out exactly what are we doing with the structures. What is inside the structure called N1, N2, and N3. Okay. Do we have any questions before compiling the program and looking into the program in GDB? No questions? It's all good so far? All right, so we'll go ahead and save the program first. And we'll call this one linked list, list.c. And then we'll switch to a terminal. gcc-g, that's warn all. And this is called linked list.c. Compile the program, compile just fine. GDB link, a.out, that's the default name of an executable when you don't specify -o. All right. So the first thing is I'm curious about what is in N1, what is in N2, and what is in N3. Okay, N3 is kind of easy, but N1 and N2, I want to find out what's in those things. So we can say print N1, and it shows me, well, actually it does a pretty good job decoding it, because it shows me that the V member of N1 is 16, which is not surprising. But the next, which is the second member, has an address. And that address turns out to be the address of N2. And GDB is smart enough to say that, hey, this address matches the address of something that I already know, which is the address of N2. Is that okay? So I can now say, what is in N2? So I can say print N2. And N2 has a value of 5 in the member V. And the next is pointing to N3. And N3 is pretty boring because it has a null pointer as next. So do we have any questions at this point about what's inside each structure? We have 3 structures in this case. Each structure has 2 members, and they form a linked list. Because if you start with N1, N1 says, hey, I'm not the last one. There's another node that you need to explore, which is N2. N2 says, I have a value 5, but I also point to another node, which is N3. N3 says, my value is 2, but I'm the last one because my next pointer is null. That is a very typical way in C and C++ in data structures to indicate I'm the last one. There's nothing to follow after this. Is that okay? All right. Okay, so when we run the program, I'm going to put a breakpoint on line 17 so that we can look at what pointer is for each iteration. So we run the program. Now it's on line 17. I say, okay, what is PTR? This is the first. This is before the first iteration, and it says PTR has N1 as the address. Okay. Does that look right to you? Okay. Because we initialize PTR to the address of N1 here, so this is at the entry point of the first iteration. So it's not surprising that PTR is actually the address of N1. Continue, and it already exited. Uh-oh. I put a breakpoint. Okay, where did I put a breakpoint? I put a breakpoint on line 17. It should stop there again. Okay. So let's run the program one more time. Single step, single step, single step. Okay, so let me run it one more time. It's just that the breakpoint is at the before. I'm guessing the breakpoint is before the label, so that's why it doesn't stop every single time. So this is the first time. Print PTR. It is pointing to N1. Single step. This is inside the body of the loop. This is just taking the next member of the structure pointed to by PTR and use that to update PTR itself. Okay? So if I single step back to here, I look at PTR, it should now be pointing to N2, single step, single step. Now it should be pointing to N3, single step, single step. Now it should be 0. There we go. And that will lead us out of the loop because when PTR itself is 0, it exits the loop, and now we're at the end of main. So are we okay so far with this code? Cool. Okay. So we exit, and then we try to do this in assembly. But there's a problem with doing this in assembly. I'm going to switch from this editor to VI. Close. Okay, so I'm going to look at this program again, and we'll try to convert this program into assembly. The problem with converting this into assembly is it is impossible for me to know whether it's working correctly or not. So I need to leave behind a trail of some kind so that I can tell, oh, okay, I can see it is traversing the linked list correctly. So to do that, I'm going to introduce a local variable here. So we'll say uint8 underscore t, and I'll just call this array. And it has, since we only have 3 structures here, so 3 should be enough because I just want to put the v member of each structure into an element of array. Is that okay? All right. So we say that is that. And just for this assignment, or just for this demonstration, I'm going to use an index to keep track of which one, which index we are dealing with here. So this is a slightly different concept compared to the homework assignment. I is initialized to 0. And in here, before I update PTR, I'm going to say array bracket I equals to PTR points to V. And then we increment I so that it goes to the next one. So this way I can leave behind a trail of the values that I have encountered as member V of the structure X that I have gone through as I go through the loop. Is that okay? More or less? Okay. Now before I do this in assembly, let's do it one more time in C, just so that we know that it works. So do a GCC. Uh-oh, doesn't like that. Oh, it says it's set but not used. That's okay, that's fine. That's not a problem. Then we do a GDB, and we put a breakpoint at exactly the same place on line 20. Run the program, print what is my PTR. It is pointing to N1, cool. And before we do this assignment, we want to check what is I. I is 0, not surprising. So we single step. And now we want to check what is in array bracket 0. What do you think it should have? Okay, depends on how we initialized N1. What do you think? It should have 16. And indeed, it has 16. Okay, single step. Single step. This is the beginning of the second iteration. Print what is PTR pointing to. It is pointing to N2 this time. Single step. Single step. What do you think is in array bracket 1? 5. Okay, very good. Single step, single step. PTR is now pointing to the last structure in the list. And we go single step, single step. What is in array bracket 2? 2, the last one. Single step, single step. Now PTR should be null, 0. We exit the loop. But this time I can look at the trail that we have left behind. In other words, we can now look at array and say, what is in it? Well, we got 20, 5, and 2. Well, not 20, but 16. It looks like 20 because it's octal. So we have 2 times 8 plus 0. So this is how we're going to leave behind the trail in the toy processor so that we can check whether the algorithm works or the implementation works or not. Are there any questions before we start to translate this code into assembly? No question? All right, so this is the C code, and I'm going to use mousepad to write the assembly code. Now, anytime you guys have any questions, please stop me and ask the questions, because the longer we wait, the more confusing it gets. All right, so let's go ahead and start with a JMPI to main first, because there's no choice. Okay, in the toy processor, it starts with location 0. So location 0 either has to be really the beginning of main, or it jumps to main. Because I want to preserve the order of how things are defined in the C code, so I'm just going to jump around all this stuff to main. It is not a call because the stack has not even been set up yet at this point. Okay, there's no assembly language equivalence to the struct X definition other than saying that a X structure has a V member, which is at the beginning. And then it also has, okay, I just drew this backwards. So V is at the beginning, and then we have next as the second element. I'm just trying to be consistent here. What appears to be at the upper portion has a high address. What appears to be at a lower portion has a lower address. So I'm just trying to preserve that order because that's going to be important. All right. So now we have the 3 global variable definitions here. So conventionally, whatever we encounter first has a lower address. Whatever we encounter later has a high address. So we say N3, and then it has byte 2, byte 0. Is that okay? In other words, the value of member V of N3 is initialized to a 0 in the C code. In assembly code, we are just spelling out all that stuff. In the C code, an address takes up 8 bytes because it's a 64-bit architecture. But in a toy processor, because it's an 8-bit architecture, the address only takes up 1 byte. So that's also another big difference. N2 is right below that. So N2 has a member V storing a value of 5. So we have a byte 5 here. And this becomes the fun part. Because I'm supposed to refer to N3 with the second byte, well, that's all we do. And you can see that there's no ampersand in assembly code, because in assembly code, the address, the label address itself is an address already. Okay? So that part you have to kind of keep in mind. And then we have N1, which has a V value of 2, and it has a next pointer pointing to N2. So these lines from line 5 to line 13 is implementing the global initialized structures. Any questions about this part? Mm-hmm.
So because we're doing it with like the labels and byte instructions, the ordering, like that thing at the top, that's flipped from how we would do it on the stack, right? If we were to stack allocate.
If you were to push these things on the stack, then you have to push them in reverse order. So if I were to recreate these 6 bytes on the stack, I would push N2, push 2, push N3, push 5, push 0, and lastly push 2. That is correct. All right. So now we can actually go to main and start to write main. So we have a subdd, which is not really needed, but it is here to initialize the stack pointer. And now we have to decide how many bytes we need on the stack. I'm going to preserve the code as much as I can, so I'm not going to use registers as shorthands. Yes?
In N1, it should be byte 16, right? And byte N2 on N1.
Oh, right, you're correct. So the last one is a 16, so we are talking about this one. Yep, you're right. Okay, because it's a 16 in the C code, and I'm going to do exactly the same thing. Okay, so now the question is, how many bytes am I reserving on the stack? So I'm going to draw a picture. Okay, I'm going to draw a picture. The highest byte is going to be the last local variable, which is I. The second highest byte, or the second highest component, is array. Now, how do we allocate for an array? Well, this is array 2, this is array 1, and this is array 0. In other words, array as a local variable is just taking up 3 bytes on the stack. That's all it's going to do. But you have to remember the element at the lowest index is at the beginning of the entire array, which also means array bracket 0 has to be the one with the lowest address. Is that okay? And then we have we have the first local variable, which is PTR, and that is going to be over here. So how many bytes do we need in this case for my local variables? Looks like 5 to me. So to allocate for the local variables, we have to subtract 5 from the stack pointer. So LDIA with 5, subtract A from D. This is to allocate for local variables. Is that okay? So I'm just lumping, allocating for all the 3 global variables into one single subtraction from the stack pointer. Okay, next, we need to initialize PTR with the address of N1. Okay, N1 is not the issue. That's how we get to N1. Because N1 is a label definition already, and the label N1 is a symbolic name of the address of that byte. In other words, N1 is the address of this byte already. So the ampersand operator doesn't need to be translated because we get to the address first in assembly. We don't get to the value first in assembly. Okay, so that's the right-hand side done with the right-hand side. The left-hand side is PTR. So now we have to be kind of careful and go like, okay, where's PTR? PTR is supposed to be the lowest of all the local variables, which is also coincidentally pointed to by which register at this point? D, because the register D, the stack pointer, is always pointing to the last thing that you either allocate or push. And that turns out to be local variable PTR. So that means a single store instruction followed by the LDI is going to get this job done. So I'm going to put the comment here to indicate which this is concluding this line in C. All right, next line is to initialize I with 0. So if you're not comfortable keeping track of registers and whatnot, you can always just kind of redo the calculations. But in this case, I is all the way up here, which is 4 bytes from where D is pointing to. I should not do any type of increment or adding to register D because I'm not ready to give up any content on the stack. So to do this correctly, I have to do a copy register, and I'm going to use register C to get the job done. But whenever I do this, I'm going to say register C is now the address of PTR. And we do LDIA with 4. We add 4 to C, so that now C is the address of I. Is that okay? So register C is originally pointing here. If I add 4 to it, then it points here, which is pointing to my local variable I. Okay. And I want to store a 0 there. And so we can do something like this. Okay, we can do a LDI works, but sub AA works too. Question?
I was just going to ask, would it be any faster if we just did a sub CC and then decremented CC where I was at?
A sub CC.
To initialize C to 0
Uh-huh.
and then decrement it once, wouldn't that put us in the same spot as I?
Okay, so that will work, but only when you're in main.
Okay.
What I'm trying to do here is going to be universal. So even if this is not main and some other subroutine, this will still work because I'm not making any assumptions.
Okay.
Yep.
Would it still work to do like to load C with 4 and then add D to C and store it in C?
Load C with 4, LDI C4, and then,
And do add C D? So it would be like C plus equal D kind of thing?
yeah, that'll work. Yep. Yep, that's a simpler way to do it. Yep. Okay. But we do have C being the address of I at this point. A is 0. So we need a store instruction to what C points to with A. And that concludes I equals to 0 in C. Are there any questions at this point? You can see how it is really kind of cumbersome because we have to calculate the address of the local variables with another register, and then we do the dereference to store to the local variables. But this is actually what is happening in your x86 architecture as well. It is just that the instructions look a lot simpler because they are not RISC instructions, they're CISC instructions. Yep?
So considering the game you showed earlier, I was wondering if people will go through their assembly code of their programs and like try and change it to make it more efficient.
I wouldn't try to make it more efficient at this point.
I mean, like advanced programmers, they're trying to.
If this were a real processor architecture and GCC is retargeted to work with this particular processor, the compiler in many cases can figure out more efficient sequences of instructions to get something done compared to a person. So, at this age, I'm going to leave optimization to the compiler. Unless you're hand coding assembly, then it's a different story. Okay. All right, so we are now ready to move on to the while loop. Okay, so with the while loop, sorry? Huh? What about the array?
Do we have to initialize the array?
Nope, the array is uninitialized. So that's a good point. The array is not initialized at this point. So if this is not main and some other subroutine, the stack can be quote unquote dirty at that point. So the actual content of array is really just assuming whatever content so happens to be in those locations when we allocate it from the stack. Okay? Which is another way to kind of sniff around, to find out, if you can use a breakpoint. And well, it's more difficult than that, but it's one way to kind of look into the stack. Okay, so at this point, we are now at the beginning of the loop. So we have a while begin. We always have a while end. And at the while end, we have an unconditional branch back to the while begin. And then we can go back here and specify the condition to get out of the loop. So you can see when I write my code, it is not linear at all, which also means if you are copying onto your notes here, it's going to be difficult because I keep inserting stuff and whatnot. But it also reflects when you are writing your code in assembly, this helps to keep it structured. Because I'm not going to fill in what I'm doing in the loop until I'm done with the control structure of the loop itself. And I'm using indentation to help me keep track of, okay, is this in the loop or is this out of the loop, and stuff like that. Okay, so the loop itself just really wants to find out whether PTR as a variable is 0 or not. If PTR is a 0, we get out of the loop. Otherwise, we stay in the loop. That's basically what it needs to do. All right, so that means we need to get to PTR. PTR at this point is still pointed to by register D, which is rather handy. So we'll just go ahead and make use of that fact. So we'll say LD, you can put it into any register, A is fine. Okay, so A is now actually PTR, not the address of PTR, because D is the address of PTR. By dereferencing D, we get to the actual PTR. And we know this trick already. Okay, you can do an AND. So this way we don't have to put a 0 into another register and then compare. This combines those two instructions, because we just need to set or reset the Z flag to find out whether A is 0 or not. Okay? And it is just kind of handy that we have JZI as one of the instructions, so that we can just say that if A is null, or when PTR is 0, we get out of the loop to while end. Which means this is the actual body of the while loop. It's the beginning of the body of the while loop. So we go back to the C code, just kind of scroll down a little bit, and then we implement the body of the loop. Okay, first line is, okay, the first line involves several concepts. The first one is, let's deal with the right-hand side first. The right-hand side is saying, how do we get to member V of whatever structure that PTR points to? Okay, well, first of all, we need to get to PTR first. Not an issue, because register D is still pointing to PTR. Okay, cool. And then we have to say, what is the first member of the thing that it points to? Well, it looks like we need to dereference whatever PTR points to. Okay. Do we have any register that is currently storing what PTR points to? Let me ask that one question one more time. Do we have any register that is storing what PTR is pointing to? What is register D? Register D points to PTR. What about A? A is PTR. So we do not have any register that is currently storing what PTR points to. Okay, so I'm going to write this down because it looks like this is kind of important, right? So I'm going to say D. Okay, I'm going to use C notation here because that's the most clear way to state it. D is the address of PTR. A is one step dereferenced. So A is PTR, but we do not have any register that is storing what PTR points to. Okay, but we don't necessarily want to know what PTR is pointing to, because we're trying to access a member of the structure that is pointed to by PTR. But what member are we accessing again? We're accessing member V, which turns out to be the first one. So the first member of a structure is at the very beginning of the entire structure. So that means whatever PTR or whatever register A points to is the thing that I want. Okay? So that's what we're going to do. So we can do one more dereference, which is LD, because we're reading. And I'm just trying to figure out whether PTR is something I want to keep. It does look like that's something I want to keep, but we can always recompute it later. So I'm not going to, I won't worry too much about it. So now A is PTR. Okay, I'm going to write it in this way because it is just more clear what we are talking about. So because I'm dereferencing A is PTR, so that means when I put whatever A points to back into A, register A is now member V of the structure pointed to by PTR. Yep.
So if it were like N1 PTR right now, then it would be like the B member of N2 kind of thing?
Nope, it's still N1. It is still N1. We have not changed PTR itself yet. Yep. So that's the entire right-hand side. Right-hand side has got A, storing it. So now I need to compute the address of element I of array. Okay, how do we do that? Well, let's figure out what is I first. Okay, seems like that's kind of important. Okay. Now, if you think that you're going to run out of register and you need register A for that calculation, what are you going to do? Push it on the stack. Very good. Okay, so I have a strong suspicion that we might need that. So I'm going to push it on the stack. Push that on the stack. So now I can use register A again, because I can always just pop it when I'm done with calculating the address of the left-hand side. Okay, because I don't want to have that thing in my mind going like, you cannot use a certain register. Okay, now I can use every register except for register D. So first thing first, I need to get to I first, right? Okay, so where's I? According to this here, I is 4 bytes away from where PTR is. Now, this time we have to be careful because register D is not pointing to PTR anymore. Register D, the stack pointer, is now pointing to something that I just pushed on the stack. So I now have to keep track of all of that stuff. The D is not pointing to the first local variable anymore. So now I need to do a CPR, CD. Oh, okay, wait, never mind. I'm going to use your technique. So I will figure out the offset first. And in this case, the offset is going to be 4 plus 1, which is 5. And then we do add AD, so that now A is the address of I. Do a dereference. Okay, so we do a LD A, so that A is actually I. And now we need to calculate where's the beginning of the entire array. Well, the entire array is 1 byte from PTR, which means it's 2 bytes from D. Okay. So this is the tricky part in C notation, because you can say A equals to array, because whenever you refer to an array, you're referring to the address of an array. There's no way to specify the value of an array in C. Okay? But if you say the address of array, I believe that syntax is equally correct. Okay, let me back up a little bit here. This is a notation issue. The notation issue is, okay, I can't demonstrate it here because I don't have that concept in C, but I do need to use that concept in the comment of the assembly code. When I use this notation, A equals to array, it means register A is the beginning, is the address of the beginning of the entire array. Okay? All right. And then what do we need to do? Oh, I just destroyed something that I needed earlier, so I'm going to put a B here. There we go. Sorry about that. So A is now I, and okay, fix the comment also. B is the beginning of the entire array. So the only thing I have to be careful now is what is the number of bytes per element in this array? Because I need to multiply that. Okay? Aliens. So what is the number of bytes of each item in the array? 1 byte. So I don't need to multiply anything. So that means I can just add those 2 items, right? So I can now add B to A to B, doesn't really matter, okay? But at the end of this operation, A is now the address of array bracket I. Is that making any sense? Okay. So I got the address, but the value that I need is on the stack. Okay, so we need to pop it on from the stack. So we do a LD first, put it into register B. So the B is the value, the right-hand side. But remember to increment D because we need to remember to deallocate that byte that is on the stack. So now we can just do STAB in order to implement array bracket I equals PTR points to V. Yep, so that's kind of a little bit long. Because that one single line in C is basically all these lines in assembly. Now, that might be slightly faster way to do it because I can see there are some additions here that doesn't need to happen, but the concept is there. Are there any questions? No questions? Yep.
But that's all just one array access to like assign a value in an array, right?
This is all corresponding to this one single line here.
Should be like find the address at the start of the array, the offset to whatever element, add them together, and then perform whatever assignment of the address you got from that.
Yep. Now there's some extra code that doesn't need to be here because I haven't used register C at all. So I really did not need to push the value on the stack and then pop it later. But the concept is still the same. I mean, you have to compute what is on the right-hand side, compute the address of the left-hand side, and then store it in a dereference way. Okay, line 2, plus plus I. How are we going to do it? I is the last one, and the stack pointer is now pointing back to PTR, right? So LDI A with 4, add D to A, so that A is once again the address of I. Then we need an LD instruction to B, so the B is the actual value of I. Increment B, so the B is I plus 1. And then we're going to store it back, STAB. And this completes I equals I plus 1, or I plus plus I. Is that okay? So one single auto increment in C boils down to this much code in assembly. Okay, one more line to go. PTR gets PTR next. Okay, so we have to deal with the right-hand side first. Okay, so PTR next. So we have to get PTR first. PTR is easy because D is pointing to PTR at this point. So we just do a single dereference at this point. So the A is PTR. But this time it's a little bit tricky because if I just say, okay, let's dereference A because we are looking at the structure pointed to by PTR, well, that will give you the value of the first member of the structure pointed to by PTR. I don't want to do that. So what I need to do is to adjust A first so that A points to member next of the structure pointed to by PTR. And how do we do that? Next is the second member of the structure. The first member has a size of 1. It takes up 1 byte. So how do I find the second member of the structure? We increment A, right? Okay, so I would like to point this out too. This is also the address of PTR points to V. Is that okay? because this is kind of important to point out in this particular format. PTR, which is a pointer to a structure, in this case, is also the address of the first member of the structure pointed to by the PTR. Is that making any sense? Okay. So by incrementing A, it is now pointing to whatever is after the first member, which is the member that we need to access. So A is now is the address of the second member of the structure pointed to by PTR. Is that okay? And we need to refer to its value, so another dereference. So A in this case really is PTR next. Okay, that's my right-hand side. Left-hand side is just PTR. And who's pointing to PTR? Register D is still pointing to PTR. So that means a store to whatever D points to is going to complete this entire operation. Is that okay? And I believe that should be okay. So that completes the body of the loop, and there's really nothing after the loop except for cleaning up. So we'll clean up. First, we specify a return value, which is totally not really needed. Well, let's see. Yeah, we have to specify the return value first, which is a 0, and then we clean up the stack. When I say we clean up the stack, we mean that we are deallocating all the local variables from the stack. How many bytes did we use on the stack for local variables? 5. Okay, so we're going to add 5 to it. So we'll do a LDI B5 and then add it to the stack pointer. That should balance the stack. And then the halt instruction ends the entire thing because this is main and I really don't have a place to return to. And we're done. Or should be.
Do we add B to D?
Hmm?
Should we add B to D, not A to D?
Oh, right, B to D. Thank you. There we go. Good job. All right. Shall we give it a try? Okay. Control A, Control C, and then we go to the assembler. And then we can delete this stuff. Paste. Okay, doesn't seem like it has any problems. Okay, looks good. And then we download as linked list. And then switch back to Logisim. Oh, kind of, when I changed the resolution of the screen, I think that kind of messed it up. That's okay, we'll just restart it. I'm going to check on OBS, make sure that we are still recording. Yep. Load the program in. Well, should I be lazy or not? Should I leave behind a long trail of execution? Or just go for it? I'll just go for it now. I'll demonstrate bad programming practice. How about that? I'll just be hoping. Cross fingers, right? Okay. Control K. And the program has stopped, okay? Okay, first thing first, we need to check the stack pointer because the stack pointer should be balanced. It should be a 0. So go to the register bank. Register is 0. That's a good sign so far. And then we go back to main. The second thing we need to check is what is in the array. Okay? And I can do the counting, but since the assembler has that number already, so I'm just going to look into the assemble tab. And then we look for the definition of array. So we go forward. Oh, I don't have array actually allocated. There's no symbol here. So I have to actually calculate it by hand. All right. That's okay. We can do it by hand. All right. So where is the actual array in memory? We have I as at location 255, and then the 3 locations before 255 would be the array. So that means it should be the highest, the last element is going to be 254, the second highest element will be 253, and then the lowest element is going to be 252. This is 255, 254, 253, 252. So we have 16, 5, 2. Is that the sequence of values in the linked list? I think it is. Okay, so we got that. So it looks like the subroutine is working. I mean, main is working correctly. So is that okay? Are there any questions about this program? Let me go back to the code in C. Nope, not this one. That one. And the assembly version of that code. So are there any questions about this particular program or the assembly language implementation?
Can you scroll to the bottom?
To the bottom. On this one, right? I can maximize it, make it a little bit taller. Too much. It automatically maximizes when I touch the top. There you go. Yep. The last line? You mean in the assembly code? It's all getting recorded. I can upload this file too. Are there any questions? How many people have seen this kind of use of structures as a initialized structure and not allocated from new or malloc? Okay. Oh. It's good for this kind of demonstration because it has initialized values. I'm basically statically defining a linked list by hand. Any other questions?
Could you post the assembly code onto the
Yep. Let me save both the C and the assembly code. So I'm going to save this one as temp list.ttpasm. And let me get out of this one. I'll even give you the CSV, the RAM file that's ready to be loaded and run. Uh-oh. Zip. Oh, okay. I think it's just that without the -a. There we go. So I upload a zip file. It contains the C version, the assembly version, and even the assembled version. And let's see, where is my window? This one.
Do you know what zipping a file actually does?
Hmm?
Do you know what zipping a file actually does?
It involves a few things. First of all, there's a way to include multiple files into one single file, which is, I guess, that process is archiving, and then there's compression. So there are two kind of distinct steps to zipping a file. In Linux, there's a almost equivalent popular command to do it. It's called tar, T-A-R, which stands for tape archive. So you can generate just a regular tar file, which is basically, it's not any smaller, there's no compression, but you can be potentially traversing folders and files inside folders, inside subfolders, and so on, into one single file. So it turns multiple files into one single stream, which is very handy for a lot of things. But you can also specify compression standards in order to make it smaller. And zip just does both at the same time. Okay, zip file, open, add item. There we go. There you go. So the sample program is now on Canvas. But the concept is more important. The code is great. I mean, if you can just kind of reference back to it and go through the video, but then you have the full list in front of you, that makes it kind of handy because now you don't have to scroll around. Both the C and the assembly versions are full list in front of you. But in terms of concepts, are there any questions about the concept of that particular sample program? Yep.
Could you go over line 46 for the assembly?
Okay. So we got the, okay, I need to go back to the assembly code first. Do you want to go back to the C code or just the assembly? Oh. Okay, there we go. Which line again? 46. This line? Okay. So before this line, what do we know? We know that register A has the value of local variable I, which is our index. We also know that register B is the address of array itself. Is that okay? So by adding those two, I now have the address of element I of array. Is that okay? Now that, in other notations, it is also the same as that, by the way. Do you guys know that? I mean, in C and C++, when you perform arithmetics on a pointer or an array, this is the address of element I of array as well. It's just a different notation, but it means the same thing. Are there any other questions? If there are no questions, then I will open up the homework assignment. Now the first lab, the early lab people have seen it already, which is okay. You can also ask questions. So the code that you need to implement in the homework assignment is kind of like this one. And in the early lab, we talked about, how we can do, what we can do to simplify this. But other than that, does that look like something that is similar to what we have done today in class? Is it harder or easier? Okay, so let me copy and paste it first, and then we'll work on the simplified version of this code. Okay, so we got it here. Okay, so we are talking about the implementation of this code. It is simplified, but it still works the same way as the original code. Minor differences is, we don't traverse some of the, This code will be a little bit lengthier in terms of execution time, but not by much. So now the question is, when you compare this code to the program that we just wrote today, let me go find the source code of that. Nope, that's not the one. That's the assembly version. Okay. Okay, so when you compare what you need to do, which is this code here, to what we talked about, just earlier today. Okay, let me see if I can display these two side by side. There we go. More or less, close enough. Which one is easier? The gray portion of the mousepad, or the one in the VI window? The VI window is easier? Seriously? I mean, this line is not easy.
The mousepad one has a whole tree thing going on.
Sorry?
The mousepad one has a whole tree thing going on. The one in VI's got just like a linked list.
Yes. But from the code perspective, I mean, line 5 and line 8.
That one doesn't have recursion. This one does.
And why would that be? Okay, so with this one, the main is already given to you. In other words, I'm already giving you some code of the invocation of traverse. Now, it is definitely not the same, because in this case, N1 is a statically defined global, so it's not a particular member of a structure pointed to by pointer. This is a local variable, which is here. That one is a parameter that is given to you. So from that perspective, it is about the same. In this code, we have a loop. In this code, we have a conditional statement. The conditional statement is slightly simpler because there's no loopback, but you still have to evaluate the condition and stuff like that. So, having all of that stuff combined, what do you think? If I showed you how to do main in the class, how does that compare to here? The only complicated part is kind of this statement here, because it has the double dereference of array, because array is a pointer to a pointer to an unsigned 8-bit integer, as opposed to the C code, where it has array being a local variable, and I'm using indexing to get to the element that I want to get to. But that's pretty much the only main difference between the two programs. So are there any questions about the traverse subroutine? Yep.
So when you have 50 in the sorted array, is it like, does it mean we have to allocate 50 bytes of memory? Or
Yep. But you don't need all 50 bytes. You just need some bytes, but not 50. You just need enough bytes to store the number of structures that is already supplied to you in the program. But if you're in the late lab, you will get your own chance for me to explain this code.
That double dereference for array, you can just do two asterisks the same way, right?
Yes.
Without parentheses.
Yep, that is correct. Yep.
That makes it much easier to read.
Oh, without the extra parentheses?
Well, no, the parentheses makes it easier to look at.
Okay, so without the extra pair, it works the same way. With the next line, it works the same way too.
It's weirder, but
I just like parentheses because they indicate what I need to do first, then I need to do what, and so on. But yes, but in terms of syntax, this is already specifying what I need to do. Yep. All right.
Sanctuary has like a good document that has all that stuff, describes all of it.
To describe.
To describe like what the asterisk does, and we have like asterisk and ampersand.
Oh, okay. Okay, the first time we call the subroutine from main is we are passing p sorted, or the address of p sorted. P sorted itself is initialized to sorted, and sorted is an array. So p sorted is the address of a unsigned a-bit integer to begin with, and since we're passing the address of that, so that means as a parameter, array is a pointer to a unsigned integer. Now, this program is not really that much harder compared to the code that I wrote today. In some way, it is easier because there's no array indexing. There's double dereferencing, okay? But if you know how to do dereferencing, double dereferencing is one more instruction. So it's not difficult. It can be tricky, okay? So my question to you, my challenge, or the main challenge of this homework assignment, is how are you going to write your code, and how are you going to test your code? What do you think? So I'm going to guide you through, but I want you to think about it first. How do you get started with writing this code in assembly? Sorry? Say that one more time. Okay. You want to write it in a way that you can debug, test, and then go back and write some more code, debug, test, and then go back to write some code. In other words, you have to do it in steps. So what do you think would be the first thing you're going to do? So what I would do, okay, no, not necessarily what you're going to do, but what I would do is to take out the recursive part. Okay, so I'm going to take out this part, and say, okay, does that work? Because if this works first, then the recursive part is actually the easy part. Okay, if this works, then I'm halfway there already. So now what you need to do is to figure out, okay, without recursion, what is this going to do with the main that we have here? What do you think? Okay, so let's track this down with commenting out the recursive part. Main is saying, okay, we'll pass the address of n1, which is this structure here, as the first parameter. We're going to pass the address of sorted, p sorted, as the second parameter. Okay, and p sorted is initialized to point to the beginning of sorted, and then n1 is the first structure, which is this one. It has a value of 5, but these two, they do not even matter because we are not tracking those down. Is that okay? So now we go to the subroutine. Okay, the first part is to say, is PTR null or not? In other words, is the address of n1 0 or not? What do you think? It's non-zero. Cool. So we go in, and then we go evaluate line 6 because the other line is commented already. On line 6, we evaluate the right-hand side first. What is PTR points to? What is the value member of the structure pointed to by PTR? It's a long way to say it. But what is it? It's n1's value, which is 5. Okay? So the right-hand side of line 6 is really just 5. Where are we storing 5? We're storing 5 to the thing pointed to by the thing pointed to by array. What is array? Array is the address of p sorted. What is it pointing to? P sorted. What is p sorted pointing to? Sorted. So we are really storing the 5 to sorted. But when you say I'm storing a single value to an array, you're basically saying I'm storing that value to the first element of that array. Is that okay? So that means I'm expecting after line 6 that the first element of sorted as a local variable of main should be 5. Okay? So if I really want to debug this program really step by step, I'm going to comment. I will comment out that line too. Just to make sure that I can store that 5 into the first element of sorted. Is that okay? If that works, I would first uncomment this line here. What is that going to do? What is line 7 going to do in addition to what line 6 is also doing? So that means the local variable p sorted is going to be changed so that it points to the second element of sorted. Is that okay? So I would check that too. Because without recursion, the program is going to terminate relatively quickly. And we're only using one of the structures that is going to be defined. So we're focusing on one single thing. If this program works the way that it is specified here, then I will remove the comment of these recursive parts. Now, it's okay to remove only one at a time or remove both at the same time because they are almost identical code. But then I don't know what this program is going to do. How do I check the behavior of my assembly code versus the quote-unquote correct behavior of this code in C? That becomes the next question. Well, this is not complete. Okay, I'm only giving you the example of defining two of the some number of structures because that is a part of the questions. I'm not going to tell you how many structures there are. But from this, okay, compared to the question itself, okay, so let me show you what the question is. This is how we defined all the structures in the question itself. And I'm giving you the first two. Do you think you can define the rest? Finish the rest in C code. Now, once you finish the rest in C code, what are you going to do? Run the C program. Okay? Run the C program, then you can figure out what is the actual result of the C program. Then you have something to compare to in your assembly code. Is that making any sense? So what I'm doing right now is really just kind of guiding you through the process of how to write this program, how to write it in steps, how to debug it, what to check for, and just kind of do it step by step. I would not do it in a way like this. Write this entire program, okay, and then run it with all the structures defined. Unless you are very, very good at data structure and also programming in TTP-ASM. Now, I can almost confidently say that I am better than any one of you when it comes to TTP-ASM. Now, if I'm using the i386 architecture, I cannot make that claim because there's a potential that some of you might have done industrial programming using that processor because it's a commercial processor. But when it comes to TTP-ASM, it's not a commercial processor. No one knows about Tak's toy processor except for Tak and students who have taken his class. So I have done this for a lot longer than you have, which means if I can make that mistake that you guys corrected in class, you are more likely to make that mistake as well. And that's why you have to write your code in small steps, debug, test, debug, make sure it works right, write some more, test again, see if it works. Okay? Because if you write a lot of code and it doesn't work, you have no idea of which line is causing that problem. If you're only writing a few lines of code each time, you know what it is supposed to do, but the program is not doing what it is supposed to do, it has to do with those few lines that you just wrote. So that's the idea of going slow, but in the end, you might be saving time. Is that okay? Yep. On line 8, it is referring to member R of whatever of the structure pointed to by PTR. Yeah, it is part of the question. So the earlier part of the question defines what a struct is. So you can see that the value is the first member, L is the second member, and then R is the third member. And this one, oh, okay, so I might as well say that too, because the first lab already has seen it, but just in case you might have forgotten, the starting point of the structures and pointers assignment is already here. So I have already implemented main, the static initialization of the structures, and also the entry point of traverse. So what you need to do is to, okay. It doesn't know how to open it. Okay, I got one already in my code, and that's why it's saving a second version. Okay, so this is struct.ttpasm. So I've done main already. Main is already implemented. The initialized structures. Oh, this is the wrong one. Uh-oh. Uh-oh. This is not good. Did I upload the wrong file? Okay, this file. Nope, this is the wrong one. I think I have uploaded the wrong file to the server, and because I just. Okay. The timing seems right. But it is not the right content. Uh-oh. But I recorded the whole thing, so worst come to worst, you guys can copy it from the video. But I'll try to get it back up again. Okay. I'm going to stop the lecture at this point, and I'll see the late lab at the lab at 8:30. As I look for the. Yep, we got it back. Save. I uploaded the wrong file. Could be worse. Okay, I'm just going to double check this one. Struct-1. Okay. Okay, this one is correct. Okay, cool. All right.